For the last video in our unit on radical expressions, we're going to talk about complex numbers. Complex numbers, or imaginary numbers, are how we simplify square roots of negatives. Our imaginary unit is I, and it's equal to the square root of -1. If I is equal to the square root of -1, then I squared is equal to -1. All complex numbers are written of the form a plus bi, where a is called our real part, comes first, followed by bi, or the imaginary part. Now, this structure, the a plus bi form, is going to be really important when you're working on online software such as MyMathLabs. They expect your solutions to be written in this form. So using our imaginary unit, let's simplify a few radicals. The square root of -16 we can break up as the square root of -1 times 16. The square root of -1 is I, the square root of 16 is 4, and rather than leaving it as I4, since none of us like that anyway, we're going to write it as 4i, just like we would if it was a coefficient on a variable. The square root of -3 times the square root of -7. We want to simplify these radicals first. The square root of -3 is going to be I times the square root of 3, because that -1 is going to factor out as that I, like we saw in that last example. The square root of -7 is going to be I times the square root of 7. And now we can multiply through everything on the outside of the radicals, everything underneath the radicals. So we've got I squared, I, times the square root of 3 times 7 is 21. And here we need to take care of the I squared. Remember that I squared is equal to -1. We need to substitute that back in anytime we see it. So this is equal to negative square root of 21. Now, I've added a note here. For this example, it's important that we simplify our radicals first before we multiply. I'm going to show you why that's so important. So don't write this down, but you can just follow along and watch. According to that product rule of radicals, since these have the same index, we could technically multiply the radicands. When we do that, we get the square root of -3 times -7. And what's -3 times -7? Well, that's the square root of +21. Where did that negative go? Okay, the negative was there in the original problem, and as we saw in our first attempt, when we simplified first, factoring out the i's, we ended up with an answer of negative square root of 21, which is the correct answer. This one, the just square root of 21, is not correct, and that's the importance of making sure that you simplify those radicals before you multiply through. Perform the following operation. 5 plus 2i plus 4 minus 3i. Now this example always gets my students. I talk about it just like I'm doing right now. Hopefully it won't catch you guys. But when we look at this, this is an addition problem. What a lot of students see is 5 plus 2i, 4 minus 3i. And we try to FOIL. Okay? But make sure you guys are paying attention. This is just addition. The presence of the parentheses is what tends to throw students off. The reason why we have parentheses is because although we're going to combine like terms, this 5 plus 2i is one complex number, which we are adding to a different complex number of 4 minus 3i. When we combine them, we combine like terms. So the parentheses in the next line are going to completely go away. So we have 5 plus 2i plus 4 minus 3i. And we combine like terms just like we would if these were variables. 5 plus 4 is 9. 2i plus 3i is -i. Again, please don't get caught. Don't get tricked by that plus sign. It's not really a trick, but this happens every semester where students see this and they just want to multiply. They see an example that looks like this, and they're not paying attention to the presence of the addition symbol. 6i minus the complex number 2 minus I. If I'm taking away this entire complex number, I'm actually taking away the 2 and the negative I. So we are going to distribute just like we did when we were using x or y variables. So we have 6i minus 2 plus I. And we combine like terms. We see the 6i and the I, and we get 7i minus 2. If we leave it like this and we're using an online homework system such as MyMathLabs, this is going to be wrong because this is not written in the correct form of a complex number. Remember that a complex number must be written in the form a plus bi. So they want the imaginary part second. So the correct answer is negative 2 plus 7i. One minus 2i squared. Remember that when we have a binomial being squared, our first step is to write it out twice. And then we're going to FOIL. 1 times 1 is 1. 1 times negative 2i, negative 2i. Negative 2i times 1 is negative 2i. Negative 2i times negative 2i is going to be positive 4i squared. You're multiplying negative 2 times negative 2 and I times I. Now here we see like terms, so we're going to combine those. We have 1 minus 4i plus, what we need to recognize is that I squared. Anytime we have I squared, we need to replace it with negative 1. So this is 1 minus 4i minus 4, and we can combine our constants, negative 3 minus 4i. Six plus 5i times 6 minus 5i. We've seen binomials like this in other chapters. We hopefully remember the term. These are called conjugates. And let's see what happens when we multiply these conjugates. We should remember that when we multiply them, the middle terms are going to cancel out. But if not, we'll see that in the steps for FOIL. So we have 6 times 6, which is 36. 6 times negative 5i is negative 30i. 5i times 6 is positive 30i. And 5i times negative 5i is negative 25. Negative 25i squared. So our original guess was correct. These are going to cancel out, and that's always true with conjugates. We've seen enough examples of them that we should know that. But let's keep going. Let's keep simplifying. 36. Here I see that I squared, which I'm going to substitute with negative 1. So I have minus 25 times negative 1. A negative times a negative is positive. So this is the same as 36 plus 25, which is 61, I believe. Yep, that looks good. So one other thing that we want to observe, when we multiplied these conjugates, and they were complex numbers, when we multiplied the conjugates, our answer was no longer complex. It became real because we lost that I component. Something to maybe remember if we're trying to get rid of i's somewhere. 3 plus I divided by 2 minus 3i. As you may have guessed, we cannot leave an imaginary number in the denominator of a fraction. So we need to rationalize the denominator and make it real. So how can I get rid of this I? I've got 2 minus 3i. Think back to that last example. When we multiplied conjugates, all of a sudden all the i's went away. So if I multiply this denominator by 2 plus 3i, I know that I won't have any more i's in the denominator. If I multiply the denominator by 2 plus 3i, I must also multiply the numerator by 2 plus 3i. So it looks like we're going to be foiling for a while, so let's get started. The next step, I'm just going to FOIL. I'm not going to combine any like terms. In the numerator, 3 times 2 is 6, plus 9i, plus 2i, plus 3i squared. That's the numerator FOILed out. I'm not going to do anything else yet with that. And now I'm going to jump to the denominator, do the same thing. 2 times 2 is 4. Now, in my outer and inner terms, we should get opposites, which will cancel out. Let's check. Plus 6i minus 6i. Yep, those will cancel out. So I don't really need to write them down if I recognize that. And my last terms, negative 3i times positive 3i, negative 9i squared. So in the next step, I'm going to start simplifying by combining like terms. I'm also going to replace my I squareds with negative 1. So we have 6 plus 9i plus 2i is 11i. And then this is 3 times negative 1, or negative 3. Over 4, negative 9 times negative 1 is positive 9. Simplifying further, 6 minus 3 is 3 plus 11i over 4 plus 9 is 13. Now, again, the emphasis on our complex number being written in the correct form is a plus bi. So we actually want to split this up. This is 3 over 13 plus 11 over 13i. Remembering that that denominator is a denominator to both terms in the binomial that's in the numerator. Six over 5i. This one is less complicated because we don't have that binomial in the denominator. So if I want to get rid of the I, maybe we're thinking similar to a radical, we just multiply by the denominator over itself, and that will work. So let's see what happens when we multiply by 5i over 5i. 6 times 5i is 30i. 5 times 5 is 25. I times I is I squared. I'm going to replace the I squared with negative 1. So we've got 30i over 25 times negative 1, or negative 25. And we should see that the 30 over negative 25 will simplify. Both are divisible by 5. So this is going to become negative 6i over 5. And I brought that negative to the numerator. You can also put it out front of the fraction. We just don't leave it in the denominator typically. Now, over here, I'm just going to show you another approach to this problem. It's not very different. 6 over 5i was what we started with. But if I look at this denominator, the only problem is really the I. The 5 is fine. That's real. So how do I get rid of that I? I can just multiply both the top and the bottom by I. So in the numerator, I get 6i. In the denominator, we have 5i squared. And there's that I squared that I needed in order to get rid of the imaginary unit in the denominator. So we have 6i in the numerator, negative 5 in the denominator. And we'll just move that negative sign, so we have negative 6i over 5. So same answer. It doesn't really matter how you approach it. Just one is maybe a few steps or one step less than the other. For complex numbers, guys, treat them like a variable. That I, you're going to multiply it with other i's just like you would multiply x's with other x's. The thing to remember, I squared you're going to replace with negative 1. When you've got conjugates, the i's will go away. So that's a technique we can use to rationalize the denominator if we have a binomial in the denominator. And then last but not least, the really most important part that we have a tendency to forget is how we write our final answer when it's a complex number. Make sure you always have the real part followed by the imaginary part, okay? So we'll see you guys next time, and good luck studying for your test on radical equations and expressions. Thank you.